Hi, I am Sohel, and today I am going to talk about Shieldywi, a runtime security framework designed by me for Unreal Engine. Both as a player and a developer, I have seen how easily gameplay systems in single player or offline games can be manipulated at the runtime. The main problem is important values like health, currency, and progressions are actually stored directly into the memory, and that makes them easy to find out cheat tools like cheat engine. So let's see an example, a very simple example. On the top right corner, we have plain health and secure health. Plain health is basically the normal float we use, and the secure health is coming from a variable of the ShieldUE. And we can see here the health, the plain health, the normal health. I'm going to call it a normal health. Normal health is 150 and the secured health is 100. I have selected defined values so that I can look into the cheat engine for defined values. Okay, so for this video, I am going to press 2 because that will deduct 15 from the health values, and both are float. So let's just do it. Let's press 2 and I can see both have taken damage, 85 and 135. Let's get cheat engine over here. And I know both of those values are basically value type is going to be float. And the value I'm going to look for 135. We are going to search for the normal health first. So let's do our first scan. And while doing it, we are just going to search for like we just need another value, so I'm going to damage once again, pressing 2, and now it's 120. Let's get cheat engine back, and now we are going to look for 120. Next scan, and yeah, I think we got it. This is the one. Okay, so this is, as I said, this is a normal float what we usually use, so I'm just going to change it to something like 999, and when I'm going to press enter, we'll look the plain health 120 will just change. Okay, it's just changed. So this is basically the normal flow to we basically use in the game programming sector. And now let's go for a new scan. The very first thing I'm going to look for is 70. This time we are looking for the secure health 70, and let's get another damage, and also we are going to get damage. The health, the normal health is basically changed. So yeah, now let's look for 55, the next scan, and here it is. This is basically 55, 55. Previous it was 70. Yeah, it was 70. So let's try to change it. I'm not going to be like, let's make it 100. Yeah, let's make it 100. So the thing is that this is, as I have said, this is basically a runtime security framework. If I press enter, nothing is going to change in the game. Yeah, we can see here over here, like this is 100, because basically what cheat engine is getting on this address is basically a trap for cheat engine. In the system, the variable is completely enclosed and encrypted with different kind of keys. So it's impossible to actually find out the value. In the game system, this is not basically 55. This is something encrypted. So yeah, this is not changing. And if we try to like change the value, it's 969 and 40. And let's get back into our cheat engine. And we can see here, yep, we can see over here, even though a few seconds ago, it actually said it was 100, the trap value, which I set, but whenever we took a damage, it's got 40, and even on the cheat engine right now, the address says 40. So let's try one thing. I'm going to freeze those values. Okay, the plain health, the normal health is basically same as the cheat engine. But here we can see the secure health is 25, and on cheat engine it says 40, because this is basically just a trap for cheat engine to find out. What if someone go through all the chains in the RAM, in the address, and find out the exact encrypted bits? What will happen then? Let's talk about that right now. I'm going to press 5, and that will basically make a simulation of tampering encoded bits in the memory address. And when I'm going to do that, we'll see how our system is going to not just going to like detect it, it will prevent the whole tampering, and it will recover this exact value, the last known valid value, into the game system. So however a cheat tool is going to try to manipulate or tamper with the value, it's never going to work. Let's see. I'm going to press 5. Tamper detected, secure health, count 1, recovered 40, tamper age 1, and the reason is integrity mismatch. Because in this system, we're not just going to like hide those values. We have shadow values, trap values, integrity check, shadow check, key check. There are so many other things, and it's just going to recover the last known value. With this tamper count and the reasoning, now the developers can easily implement soft penalty and hard penalty even in single player and offline games. And this system is designed to be used in Unreal Engine through both C++ and Blueprint system. And here are the nodes for the secure float. This is the integer nodes, and this is the bool nodes. And for this plugin right now, we have basically to initialize rule system, or basically initialize nodes. The very first one, this one, you need to use to have like a rule variable. And this one is good if you want to have like a group of floats having the same rules. Or if you want to use like a single variable having its own rule, you can also do it from here. Or if you want a group of floats having same rules, you can use this rules variable. And this thing is basically simple, like set value, get value, and this one is for validating. This is like rekey. You can change the key for the encryption, and the same things for integer and bool. My goal is to expand Shieldywi into a complete security framework plugin for single player and offline games in a way which will be lightweight, developer friendly, without any complex implementation system, and obviously educational. So the new learners and the developers can easily know about and learn about how to protect their game from tampering at runtime. Thank you.